Did anybody keep that sheet from last time? Let me grab that from you if you took that with you. Thank you. Thank you, my friend. Cool. All right, we got something big happening today. And kind of this whole week. Just like a heads up, probably the biggest web work of the year. Oh boy, it's good. Lots of practice. That's kind of what we're doing this week. So today I'm going to talk about some stuff, and then Wednesday class certainly is dedicated to working on this web work in here. It is not a small one. Like I said, it's like 20-something problems. So it'll be good practice. But there is this new web work up. It hasn't opened yet. It'll open toward the end of class. I think it's due Sunday, which should work if we dedicate time in class to it. Should have plenty of time to work on it, get help, all that kind of stuff. And let's just do a quick recap of where we're at, because I wanted to give it some context as to where we're headed. So last times, we talked about this thing called the definite integral. And that was this beast here. And we learned that this is a process of cutting things up into rectangles, finding the area, letting the number of rectangles go to infinity and getting that true result. But then we also learned this thing here. What is this called? Where f prime is little f. What is that guy called? Fundamental theorem of calculus, part 1. So this is the fundamental theorem of calculus, part 1. And this f here is the antiderivative of little f. And that's kind of where we're about to pick off from for today. Little f. And so we had this process that was painful, and we turned it into something that we could use calculus for. So the reverse of differentiation. And then it just turns into this simple subtraction over here. So one of the key things you need to learn before the end of the semester, and when you move into Calc 2, this will be one of the things we start upon, is being able to find antiderivatives for all sorts of different things, much more than just the simple ones we've looked at so far. So today, what we're going to talk about is what's called the indefinite integral. So definite integral means it's got limits. It's got numbers on the lower and upper end of the integral. An indefinite integral is essentially formula for antiderivatives. And this is where it gets hard. This is where we're going to have to change our perspective and do a lot of practice in getting these things out. So, what do I mean by that? Well, for instance, we might have this problem. So notice I didn't put any limits on there. What that means is find the antiderivative of the integrand. So when I look at this problem, it is an indefinite integral, and I know that because there's no limits on here. So I'm not going to play the same game as I did before. In part I do, but we don't have to go the full distance. So the indefinite integral. So this problem is asking, what is an antiderivative for the integrand, e to the 2x? And we've got these formulas where we put a big table, and you worked on one last week, and I just collected some of them. I'm going to write these in a slightly different way. So here I'm going to write f of u, and then over here I'm going to put antiderivative of f of u du. So this is antiderivative, and I'm changing the variable to u because it's going to actually play a role for us that makes this thought process easier, and it's the classic way to do this. So let's actually think about, what do I know how to take the antiderivative of in terms of e? And it's honestly just this thing here. The antiderivative of e to the u is just e to the u. Just think x, if x works better for your mind, think in terms of x, it's just a change of letters. And now we're going to start tossing on this arbitrary constant here. So this is a constant of integration, which some of you have already been adding occasionally to the definite ones. You don't need it on these guys. If you think about it, it would just cancel out anyway when you took this difference. But what this is acknowledging is that no matter what I add on to this, if I take the derivative with respect to u, the c vanishes in the derivative direction. So there's infinitely many possible functions that could be the antiderivative. And we just denote that by putting this plus c. We'll solve for it sometimes, but in general, just kind of get in the habit of plunking that guy down. Okay, so look, I know how to do this. So I know, or we know, this, that this is this. We have that rhythm that we understand and we believe. And what the game is for this week is to take these basic rules that we have here and convert more complicated looking things into these basic forms. So what we'll talk about today is substitution. Substitution for evaluating integrals. And we can actually extend this to definite integrals as well, and I'll show you how to do that because I've got a way that'll keep things from getting too messy for you. So we're going to view this thing here as a little box that I'm going to lay on top of my given problem. So you look at your problem, you say, what does it look like that I do know how to do? And this is the best thing, that we know how to do the closest. And I lay this on top of there, and what comes through this box is what my substitution will be. So, in other words, I've got this thing here. I want to get it to this thing here. So I'm going to let u equal the 2x. And if I replace that 2x with u, it looks just like that guy. Let me stop for a second. So the game is to tuck all the nasty details into a variable and kind of hide them away, use the rules, and then we'll come back and undo the substitution. So when you do this, so step one is identify the possible form. So that's kind of what I did here. Here's my possible form. That was step one. Step two is to identify the substitution. And this is where you let u equal the nasty part, whatever, the fugly variable stuff. So here I've done that. Step three is we have to replace this guy to get a du. So step three is find the differential change. And this is where the real work gets done. You'll have to take a derivative here. So i.e., differentiate your substitution. So I've got this u, let's put it right here, u equals e to the 2x, and now I'm going to take the derivative. But I'm going to write it a little bit differently. I'm going to use this differential notation. So when I take the derivative of the left side, it just becomes du. It will always become du. The right side, I take the derivative of e to the 2x. What is the derivative of e to the 2x? I know I'm just popping out of here asking you a question. What's the derivative of e to the 2x? 2e to the 2x, right? So this is 2e to the 2x, and I tack on this dx. So tack this on after you take the derivative. At this point, there's a couple of routes to go to convert our integral finally. But here's kind of a simple way that really you can't go wrong with. Solve step 3 for dx. So in other words, I'm going to take this step 3 thing here, and I'm going to solve for dx. And what that means is dx equals du over 2e to the 2x. Note there's a mix of u's and x's on that side, but it's okay. It's kind of going to actually help us make sure we know we did the right thing. So there's a bit of a self-checking mechanism in this. So what am I on? Step 4, thank you. Step 5 is next, yeah. So step 5 is rewrite the original integral using your u and your dx substitutions. So integral e to the 2x dx is what I started with. This is going to become integral. This is u because I said it was u. So I'm immediately going, oh, u is 2x. Now I got that. Already looks better. Less variables, less stuff flying around. And the dx is going to be du over 2e to the 2x. So this thing here is just e to the u. Notice that this is e to the u here. So CF, original sub. I'm going to show you a second way to do this whole thing. Original sub appears in dx, replace, like I just did here, or I'm about to do. So this is integral e to the u du over 2e to the u. And, oh shit, oh my God, hold on. I have kind of hosed myself here in a weird way, and I'm not sure. What the hell did I do wrong? What did I do wrong? My God.
U is 2x?
What's that, Joshua?
U is 2x?
U is 2x, yes, but that is not, I did something really quite
U is 2x?
dumb. Oh, yes, thank you, Josh. Yes, Joshua, yes, that's good. Yeah, I went too crazy, sorry. I got myself too excited trying to keep this organized. U wasn't this, U was 2x, good Lord. Sorry about that. So let's come back here. U was 2x, I forgot my original substitution. So du is easier, it's just 2 dx. And then dx is du over 2. So I forgot what my original substitution was. Sometimes it would be that nasty, but not this time. So u is 2x. I differentiate that. I've got du is 2x. And then when I solve here, this works out a lot better. So it's just this. So the dx became du over 2. Thank God. There we go. Sorry about that. Scared the hell out of me. So now, any constants that show up come out front. So I'm going to bring 1/2 out front, integral e to the u du. This whole process was for getting this 1/2 out in front, really. Now do the integral. So that was step 6. Step 6 is use your table, your formula. / table on the u form. So this is just 1/2. I carry that constant along. Integral of e to the u is e to the u. Tack on your plus c. So I'm just adding that on. Now, this thing here is almost done, but the original problem was in terms of x. So step 7 is back substitute. And I'm gonna put a note here, only if it's a indefinite integral. If it's a definite integral, we're never gonna go back, and I'll show you how that works. Integral. So if there's no limits, then you have to back substitute. And I say this because I've seen so many people do this back. This is a part where things can get weird. So I'm gonna strongly suggest you follow this advice, which you'll get lots of practice at. So in other words, u equals 2x, so 1/2 e to the u plus c is 1/2 e to the 2x plus c. And that's my final answer when I do that substitution to come back. So the whole game is tuck the complicated looking things into a single variable, use the table, use the formula, come back and put the nastiness in after you're all done. So we probably should practice some of this because, especially since I hosed up that example. Is it okay if I erase on the right side? Yeah, okay, cool. Let's leave our little table up over here and we'll add to it as we need to. Okay, I want to do a simpler one right now. So let's try this guy. Integral of 3x minus 7 to the 5th power dx. Now, one way you could do this, if you're really got some spare time and you like multiplying things out, is you could multiply this whole thing out, which would be painful. But you could get a big ass polynomial and just use the power rule. But we can make life better than that. That's a lot of work when it doesn't need to happen. So notice that this sure would be great if it looked like that. Right? Then I go, oh, it's 1/6 u to the 6th, and I'd be done. I just use that integration power rule that says this: u to some power integrates to raise the power, divide by the new power. And that's provided n isn't negative 1. Otherwise, I'd get division by 0 out front. That would be really bad. So, it looks like this. It's got this feel. When you see parentheses in the integral, your u is probably lurking inside the parentheses. So this is a good, like just an experience thing that you'll learn to see, that the u, the best bet is this. So let's go through. So thinking that it feels like that, I'm gonna let u equal 3x minus 7. And then I find my du. What's that derivative of that right side? 3. And I tack on a dx. Solve for dx. And you get 1/3 du. And now rewrite your integral. So it becomes integral u to the 5th. The dx becomes 1/3 du. And now I bring the constant out in front. And now I use the power rule. So the 1/3 comes along for the ride. The 5 goes to a 6. I divide by the new exponent, so I'll put a 1/6 out in front and tack on a plus c. and this is equal to 1/18 u to the 6th plus c. And now I'm gonna back substitute, replacing the u with what I said u is holding. It's storing something for us. So this is 1/18 3x minus 7 to the 6th plus c, and that's our answer. How do I check myself? How do I check my answer if I'm worried? Besides going to ChatGPT or something like that, how do I check it if I'm just, all the power's out? Take the derivative. Take the derivative of this, and it should turn into the integrand there. So the check would be this. Take the derivative of 1/18 3x minus 7 to the 6th. The plus c will just go to 0. We don't need to check that. So, chain rule. The 6 comes out front. So I've got 1/18 times 6, 3x minus 7 to the 5th. Now again, this is derivatives. We haven't done those in a while. You're gonna be doing them when you find your du's. Times the derivative of the inside, which is 3. So that's just chain rule. And look, I got 18, cancels with that. And we got our original integrand back. So I did it. You can always check yourself this way. Let me stop for a second, let you get caught up. Okay, let's look at something else here. Is there any questions or anything? We're feeling good? Okay, take that as you're not feeling bad. So let's try a different one. How about this guy? Integral of xe to the x squared dx. And things are starting to get weird now, because I've got multiple variables inside there. But I'm going to try to key off of what I really wish it was. And I really wish it was this, because this is like the easiest calc in the world. I hope it's that. So if it has to be, if I want it to be that, what would u need to be? What's the exponent on the e here? X squared. So in other words, I'm laying this thing like there's a little window here on top of the integral and looking what comes through it. It was an x squared. There's an x floating in there, that's okay. What comes through the u window? So I'm gonna let u equal x squared. And then I do du is 2x dx, and I solve for dx. dx is du over 2x. And now I do all my substitutions. I'm gonna rewrite it. Don't worry, I'll give you some to work on. I just want to do some of the edge case kinds of things together. So this becomes integral. I'm leaving this x alone. Notice it's not mentioned anywhere here. All I'm doing is replacing that exponent with u and that dx with this. So I'll leave the x there, and then I've got e to the u. dx is du over 2x. At this point, you need to have a pure u integral. It can't have other variables in it, but it does, right? I've got an x in there, but what can I do with the x's? I cancel these. So at this point, if there's other original variables in there, you hope they are canceling. So all other expressions must cancel. And if they don't, you have chosen wrong. This is kind of a sanity checkpoint. If your original variables aren't canceling out here, you've picked the wrong u, or maybe substitution won't work on this problem at all, which is a possibility. So in some ways, there's a lot of experience and just knowing, okay, it can't possibly be anything else. So here I'm going to bring that 1/2 out front. It did work out here because the x is canceled, so I've got 1/2 e to the u du. now I go to my table, that's 1/2 e to the u plus c. And that, back substitute, is 1/2 e to the x squared plus c. So I just replace the u with the x squared. You can check yourself with the chain rule. We get back the original. All right, let me give you one to try. And we're gonna slowly get these more complicated. There's some good tips I've got for you, but let's go a little slower first. What about this guy here? We've got integral of x squared cosine of x cubed dx. Let's try that one. So make your pick. What do you think we should shoot for? What basic form? Think about those basic tables. Cosine, yep. So cosine of u goes to sine of u. So if I can figure out how to get it into this form, we're golden. So let's shoot for that cosine form. Don't focus on the x squared. Just like right up front, I'll give you that tip, just in case. We hope the x squared comes out in the wash. U be x cubed, just in case you were uncertain of that. Feeling okay on all this stuff? I'm going to actually show you just a slightly different, it's the second way we could get this thing to balance out instead of solving for dx in just a minute. In fact, though, I will put the answer up here for you so you can make sure you've got a sanity check on that. Should be your answer. Third x cubed, or sine of x cubed. Another way to balance this out is to look at what this differential expression looks like here and force what you've got into that. So notice that we've got x squared dx up there. You can't put different, so at this point you never want to incorporate new variables into the thing, but only constants. So notice that if I put a 3 here, then I would have du perfectly if I put a 3 inside there. But you can't just put a 3 in, you got to balance on the outside. So I put a 1/3 out front, and that just gets me an effective 1. So at this point, now I could go, oh, okay, so this is 1/3 integral. All that stuff is du, the x cubed is u, and I just turn it into that. 2 routes to the same place. You pick which one feels best to you. This was actually how I learned it, and then I started teaching it with the dividing route because it seemed like it worked better for a lot of folks. Go to your table, antiderivative cosine is sine, back substitute. Get our answer. Yeah, let me, there's no questions. Let's try another one. So this one's for you. I'm gonna give you a few minutes on this one.
I have a question.
Yes, sir.
Why wouldn't you just make cosine of x cubed u?
Let's try that. I like that. Great question. So,
Because that was my original thought before you.
yeah, no, that's a great question, Sam. So here's our original problem, right? Like this. Let's do that. Let's make this whole thing u. So I'm gonna let u equal cosine of x cubed. Now du, got a chain rule. So negative sine of x cubed times the derivative of the inside, 3x squared dx. That look good? All right.
That's what I had.
Okay, so now I'm going to solve for dx. And I'm going to get
over all that crap.
yeah, du over a lot of crap. So let's do it. So let's plug it in now. Let's come to our substitution. So this becomes integral. Leave that x squared alone. Hope things work out.
It does.
And let's see. So then cosine of x cubed is our u, right? And then the dx becomes, I'm gonna put the minus out front.
Okay.
Then I've got du over sine of x cubed times 3x squared. So now when I go to cancel.
Yeah.
Yep, beautiful.
Those cancel out. You still have that in the bottom.
Yes.
So can't you just bring that out and go 1 over sine x cubed?
We can't because the variable stuff has to stay inside. The only thing that can come out front are constants.
Okay.
And so this is how I know that that was too big a choice, that I've got extra stuff floating around at this stage.
Okay.
Is that good?
Yeah.
Yeah, cool. Yeah, thank you for asking that, yeah.
Because that was my original thought.
Uh-huh.
Just make cosine of x cubed u and then go from there, but then had a bunch of crap on the bottom line.
Let's do a problem where Sam's choice was the right one. So let me show you where this choice might be the right one. So let's see, what do? We let u be cos. So let's say I've got cosine of x cubed sine of x cubed x squared dx. Now in this one, that looks horrible. Got a lot of routes I can go. So let's say that I luck out and I go, okay, God, I don't know. I'm gonna let u be cosine of x cubed. So then du is negative sine of x cubed. We did this already, right? We've got the work right there. X squared dx. So now my dx is that thing that I had, sine of x cubed times 3x squared. All right, now let's do our substitution. We never thought about this, right? Or we never thought about this, so we just let it hang. These two pieces, they're coming for the ride because we haven't addressed them at all. We just said, okay, this is u. So I'm gonna rewrite that whole cosine of x cubed as u. And then I've got sine of x cubed, x squared, and now my dx, put that minus out front. Hell, I'll just put the whole minus 1/3 out front if you don't mind. Because I got minus 1/3. And then here I've got du over sine of x squared, excuse me, sine of x cubed, x squared. And now life looks pretty freaking good.
Because then both those canceling off, all you have left is du.
That's right. And so I'm left with negative 1/3 integral u du. That's power rule. So the u goes to u squared. A 1/2 comes out in front. I already had a negative 1/3 plus c. Negative 1/6 u squared plus c. And then back substitute. And it's a beast. right? But this is one of those times when that is the only right substitution. So after back substituting, I've got, what was our u?
Cosine of
Cosine.
x cubed
Yeah, thank you.
squared.
Yes. So in this case, that would be perfect.
Yeah.
Yeah. And I tell that because everything comes out in the end. Great question. Yeah. Everybody cool with this example? Okay. Let's do a series of problems here that each one's a little bit different. I want to show you how to handle fractions because there's kind of some special things we need to do. So, this is kind of just special, well, how to handle fractions. In integrals. Okay, so, and I'm going to proceed by a couple examples here. So first off, I might have 2 over 1 plus 3x dx. Okay, here I got a fraction. When you have a fraction, if there's no parentheses in the bottom, just like here, right? There's no parentheses, it's just the bottom, just by itself. In that case, shoot for this form. So let me write this up. If the denominator has no parentheses involved. Now these aren't hard rules. There's going to be cases where this doesn't hold true. These are first attempts. Try, that's why I'm going to put try here for this form. Integral 1 over u du. In other words, the whole denominator is u. My substitution is I'm going to replace the denominator with that. So this form here, 1 over u, that's the natural log form. So I'm hoping this is a natural log. And then I'm only going to know after I get experience or I just test this thing out. So for this guy, I'm going to let u be that denominator. Can you finish this up, please? That 2 that's already in there, just bring it out front, carry it along. Good, cool. Let's talk if we need to talk. Any questions at all on that? All right. Still folks finishing up. I'm going to put 2 other ones up here for you. Let's do this guy. Actually, go ahead and try that one. You kind of have a sense, and then we'll shake him up a little bit. So you get some good successes. fraction, no parentheses. I'm gonna try for a log. Things work out pretty. Remember, your whole goal is to get a number out in front to balance this off, or to figure that there can't be a number the way you attempted things. Sometimes if things haven't canceled, if you don't get these X's canceling things out, and you're down here and you've somehow got an X still floated in here, things have gone bad. Do not proceed. People will proceed. People always proceed because they're like, well, I'm just gonna make it happen. You can make it happen, it just won't be right. Is there any questions getting up to that point at all? If not, when I back substitute, log of 1 plus x squared plus c. Let me pop another one up here, because I want to kind of want to keep rolling with this fraction form. So let's tweak this just a little. Integral x over, and then I'm going to have 1 plus x squared in the bottom, but I'm going to have cubed. Let me let you play for a minute. Give it a shot. And if you get that one done early, I'm going to put one more up here for you to ponder. It's that one. Suspense out on this one. We're going to let u be the thing in the parentheses, right? That's a good rule of thumb. So even though I have fraction, I'm still going for the substitution to be the nasty stuff in the parentheses. This will work out quite well for you. Kind of curious. Anybody work on this other one yet? What'd you think? Oh man. Sorry, I don't mess your shirt up. Your shirt's always so nice. I bring some nice gloves so I can touch you and not get your shirts, your beautiful shirts all messed up. How are we doing back here?
This is for me.
Cool, I'm excited, thank you. I'll take them both. All right, Joshua, here's another one for you. And Addie, I guess, there. That'll teach you. How we feeling this one? Is this okay? Where do I go from here? What is this? Yeah, Leo.
Would you want to take the exponent and make it negative? Let's
Yeah.
look it up.
Exactly, yeah. This is just a power rule, right? Just gotta see it as such. Yes, absolutely. Then use the integral power rule. Add 1 to your exponent. Bring that 1/2, add 1 to your exponent. Divide by your new exponent plus c. That gets you an effective -1/4 out front. U to the -2nd plus c, and then when we back substitute, and we could even rewrite this, bless you. We could even put that underneath, which I won't do it. Part of me wants to. Let's see, u was this. That's a lovely answer right there. Anybody need to talk about this first one at all? We feel good. Is this what you got, Leo? Yeah. Cool. We come to this one here, I think. Okay, look, fraction, no parentheses. Dr. T said, let u be the denominator. I do that, and I get this. How do I know immediately this isn't right? There's no x. There's nothing this is gonna cancel with. You see, there would have to be an x floating around, like there was back here. Because that x isn't gonna cancel. So this won't cancel. So this is a bad substitution. Well, let's try something else. What about, so you keep trying. You go, okay, what about u equals x? Ooh, what does that do for me? Let's see. This is du is dx. Okay, right? And I rewrite, and my integral looks like this. 1/1 plus u squared du. Oh, it's the same problem, just in a different letter. So this is a substitution you never really want to make, unless you like writing things in new variables the hard way. So you're never going to let u be x or whatever your variable is, because it just rewrites your integral. It doesn't get anywhere. It doesn't progress or hide any details. So this guy here, let's see here, I'll finish him up. How do we do this one? Because my subs aren't working. Where do I go? How do I do this? Chat GPT? Yeah, chat maybe. Leo.
I mean, don't you still replace the 1 plus x squared for u and do the natural log substitution?
So tell me what you're saying I should do? Let u be the whole denominator?
Yeah, and then take the,
But what about,
what do you call it?
well, let's see, so if I do this rewrite here, this is gonna be 1 over u, and I guess that's what you're suggesting, yeah?
Mm.
And then the dx will become du over 2x. The problem is I got that x in there that's never gonna go away, so now I'm gonna use an x's and can't really progress. Does that make sense? So no substitution is gonna make this guy work. Joshua, how'd you do it?
Tan inverse.
It's he looked at a table. You either know the table or you go to the table. It's an inverse tree. This is inverse tangent. So you have to, so if this fails after a couple subs, then you're like, well, shit, I better go look this up at a table. And there is, in fact, this whole form that says that is the arctan of u plus c. So this is another fraction to keep an eye out for. This is when this will show up pretty often. So this guy can't do any substitution, don't need to. It's just inverse tangent of x plus c. And this is from a table. And then all these folks are like getting this thing done, so I'm like throwing barrels down behind me to try to get, slow you down. Anybody make any progress on that beast? Yeah. What'd you do, Joshua?
Either 1,
Say it again.
x squared plus 1,
Yes.
or 1 plus x squared, minus,
So wait, so you did x squared plus
Yeah.
1
over 1 plus x squared?
over 1 plus x squared like this?
Yeah, minus 1 over 1 plus x squared.
Oh, you divided.
Yeah.
Okay, that's what you need to do. Gotcha. So this one is a little weird, and we've never actually done this in this class, but it's a good thing to know how to do. We can do long division with this thing. So since the top is the same degree as the bottom, and they're both polynomials, I'm going to divide into there. Now you might not have ever seen this, but it's definitely a cool thing to do. You look at your leading term. How many x squareds go into here? 1. So 1 times x squared plus 1 is this. Subtract down. These cancel. I get minus 1. And so I rewrite the whole thing to look like this. Now check this out. This is the same as this. And if you don't believe me, add them together. So 1 minus x squared plus 1 over x squared plus 1. Get a common denominator. And now you just get x squared over x squared plus 1. So that's kind of a cool trick. So rewrite this with some algebra. There's no calculus or substitution going on here. This just becomes this guy. And so now I can do this. What's the antiderivative of 1? X, beautiful, yeah. And then this, we just did it. So that's kind of cool. Is that what you got, Joshua?
Yeah.
Well done, well done. All right, let's see, I might have one more. Oh, I got a good one. Let's do a few. Let me set you up for success with your homework, because there's some tricky ones in there. And the tricky ones sometimes are these natural log ones. So let's do that. So what if I have integral of natural log of x over x? Got a fraction, right? What was the first thing I might want to think about, at least? Letting u be what? The bottom, but does that get me anywhere? No, that just rewrites it. So notice that u equals x does nothing, ever. Well, what should I try? What could I try? What else could you be?
Min x.
Let's try the natural log. So let's try U equals natural log of x. Can you take it from here, please? Give it a shot. If you let u be that natural log, your du turns into this. The only time some folks have trouble with that 1 over x. If you just multiply across by x, you get a nice substitution. And then you see you lose the x that's floating free in there, and it works out pretty well. Challenge problem. I'll come around, check on you. Sometimes your substitution's good for more than just one thing, is the hint on this one. So just think, could I use the substitution in another place as well to make life easy? Anyway, I won't say too much, it's kind of a fun one. Run the rest of it really quick, and I'll put another one up for you in case you just can't take it and you need. That's a tricky one too. These are both tricky ones, but you can do them. Right back. give you the tips just to make sure you're on the right track. Those are the subs you want to use. And I do have a hint, and this is what I meant, that once you have this, you also know that x is this if you were to solve for x. So let's say you let this whole denominator be u. Still got an x floating around in the top, but what if you rewrote that top in terms of u? So this one, we can use the substitution in two different positions. This is for the denominator. And then I can use this to rewrite the numerator. Give that a shot. And then when you do that, your du is just going to be a simple 2dx. So that's all chill. But that'll help you break it. And then the other one's similar-ish. I've already done with both of them. Oh, damn it. Yes, that all looks good. Yep.
Mine is nice, but then
Yeah, this is beautiful. Yes, sir. Yeah. I'll get you yet, Joshua. Check out my front here. How you doing, Abby? Did you get the first one? Okay, cool. Yeah, okay, cool. How to get that x equals? So I solved the u, so u equals 3 plus 3. I took that, subtract 3 from both sides, and then I've got u minus 3 equals 2x, and then I multiplied by half on both sides. So I got 1/2 u minus 3 halves equals x. So do you see how it goes? So like this, do you see where the minus 3 would come from?
Yeah.
You subtract it, and then just halve both sides.
Okay.
Yeah?
Yeah.
Okay. Anything you want to talk about, or are you good? Okay, you're confused. Okay, which one? Which one are you confused? Okay, yeah. Well, maybe I should go do it. Would that help? Yeah, I'll go do it. How about that? Yeah. I'll show you what's up. So let's talk about this first one. So I've got a fraction, no parentheses. I'm going to let u be that whole denominator just to see how that goes. And when I do that, I get du is 2dx, so that dx would be half du. Then I come down here and I do the substitution. Now notice on top, I still would have this. I haven't done anything with that, but the whole bottom's u, so that's nice. And then dx is 1/2 du. But I've still got this dang x floating in here, and it ain't canceling, right? There's nothing to cancel x plus 5 with. But if I take this equation, this original substitution, and I solve for x, are you cool with this, Jasmine, how I got the x? Is that okay? So now I'm going to sub that in here. So I'm going to put but x equals 1/2 u minus 3 halves. So when I come over here, this is going to be 1/2 u minus 3 halves plus 5 over u du. Let me stop.
You
Yeah.
missed 1/2.
Oh, thank you. Yeah, I'll put my 1/2 out front. Thanks, Sam. Yes, good call. Still looks terrible, but don't worry. I can see it on your face. You're like, I don't get it. Let's fix it up a little bit. So I've got my 1/2 integral. Now this, I can bring these two guys together. So this is 10 halves minus 3 halves. This all becomes 7 halves right here. So the top of this is 1/2 u plus 7 halves over u du. And now I've got a fraction with a sum on top. So when I've got a fraction like this, I can break it apart like this, because the sum is on top. So this becomes 1/2 integral 1/2 u over u. That's gonna be good, those are gonna cancel, plus 7/2 over u du. Now let me stop for a second because I'm not done, but Jasmine, how are you feeling on that? Yeah, does that feel better? Okay, cool, cool. So now look what, this is great because these u's cancel. So I've got 1/2 integral 1/2 plus 7/2 over u. This is just a natural log. It's 7/2 natural log absolute value of u. And this is just 1/2 u. Let me rewrite this up here. So this is, I got my original 1/2, and then this inside here is 1/2 u plus 7/2 natural log of u plus c. And I'm almost done, but I still have to back substitute. And then I'll be set up. So when I come back, well, let's do a bunch of things. Let's spread that 1/2 through, so it becomes 1/4 u plus 7/4 natural log u plus c. And now I can back substitute. And it becomes 1/4 2x plus 3 plus 7/4 natural log of 2x plus 3. So it's kind of a beast, but does that feel better, Jasmine? Like, yeah, okay, cool. Anybody want to talk about that guy? That's a hard one. Let me do this guy here. We'll call it a day. Let me see, I'll leave that all up for you. But let's do with a new pen, because this pen blows. Not a green, ooh, that's nice. All right, so, got integral x root x plus 1. I guarantee you'll run across this in the web work. Because I picked this one up, I was like, we'll talk about this, but I'm putting this sucker on. So my hint is to let u be this. So I'm gonna let u be x plus 1. And then du is dx. That's sweet. I don't even have a constant to adjust or anything, but dang it, when I do this substitution directly, look what I get. I get x square root of u du. Can't have mixed variables. How could I get rid of this x and make it into a u thing?
X equals negative u plus 1.
Or u minus 1, yes.
Minus 1.
Yeah, but that's the right idea. So same game as this other one, sub this back out, so now look what we get. You use both forms of the substitution for the u here, and then for the x here. But the key thing is, now I've got everything in terms of u. I'm gonna write that as u to the 1/2. Distribute, so it's u to the first times u to the 1/2, that's u to the 3/2, minus u to the 1/2, du, power rule. Add 1 to the exponent, you get 5/2. Multiply by the reciprocal out front. So that's 5/2, minus new exponent is 3/2, so a 2/3 comes out front, plus c. Back substitute. So your final step is to go back 2/5, u was x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. And this is the kind of shit you just don't guess. You don't look at that problem and go, oh, it's probably that. Like I don't. Maybe you do. You might, you might have amazing math abilities that I can't comprehend. Completely possible. I never doubt that that's a possibility. All right, my friends, so you've got like a gajillion of these to work. So Wednesday's a work day in here. Bring your laptop, bring your web work, let's work on it. Do as much as you want before then, but you've got quite a bit of time. Thanks, everybody. Now we only have 8 classes left.